Hello everyone, myself Priyanka and I will be presenting the PPT of signals and systems on the topic noise filtering from a speech signal. Moving ahead, we define what is noise filtering. It is a process of removing unwanted noise from audio signals. It enhances clarity, intelligibility, and the quality of speech. Moving ahead, let's have an overview of the whole presentation. Firstly, we will generate a sine wave signal, then we will add a noise to it, then we will filter it. Then repeating about two steps, we do same for the speech signal. Here the speech signal I have taken is of my own voice. Then we will verify the properties of signal, that is linearity, time invariance, stability and invertibility. To understand PPT more better, or I have mentioned some keywords that I have also used in the code of the presentation. First one is sampling frequency. This determines how many samples per second are taken from the continuous signal to create the discrete signal. Then we have fast Fourier transform. Basically, it is a tool that basically converts the time domain signal into the frequency domain signal, hereby providing more information about the frequency of the signal. Then um, we have frequency axis. The frequency axis is a horizontal axis or x-axis of a spectrum plot that shows the frequency of a signal. Then we have Butterworth filters. Butterworth filters are the filters that we have used in both our filtering of a sine wave signal and the speech signal. It helps to avoid abrupt changes in the amplitude response. Moving ahead, we have a sine wave signal. In sine wave signal, we will first generate the signal, then we will add noise to the signal, then we will have a spectral analysis of a signal. Why we do spectral analysis of a signal? Basically, we have the noise we have added here is a random noise. So, to understand the frequency range of a signal after adding noise to it, or to find the range of a frequency where we want to filter it, we will do the spectral analysis of a signal. Then we have designing a Butterworth bandpass filter. Then we will filter the noisy signal. Here are the some important variables taken. Like here we have a signal details and the filter details. We have sampling frequency 500 hertz, signal frequency 10 hertz, time duration of a signal we have taken is 1 second. The filter details, the order of filter we have taken is 5, and the cutoff frequency is from 8 hertz to 12 hertz, which can be derived from the spectral plot, like we can see later. Moving ahead, here are the signal plots. The first plot is of generated signal, the sine wave that we have generated, and the second plot is of noisy signal, like how the signal looks after adding noise to the signal. We can understand it more better by going through its code. So here is the code of the sine wave signal. First, we have defined here the sampling frequency. Then we have defined the frequency of a signal. Then the time duration of a signal. Then the signal. Then we plot it. Then we are adding noise to the signal, which is, yeah, you can see like it as random noise we are adding to the signal. Then we will do spectral analysis of the signal. First, we are collecting the signal basically. Then we will finding the FFT points. Then we are taking FFT of a signal. Then we are creating the um, frequency axis of a signal for a spectral plot. Then we are designing a filter of order 5, and the cutoff frequency we have taken from 8 to 12. Where we get the cutoff frequency, we get it from the spectral plot, like we can see in the next slide here. Then moving on, we'll filter the signal, and we will having visual comparison of the signal, like how the signal looks before and after adding noise to the signal. So moving further, we see here is the spectral plot of a signal like we get. So the peak here shows the cutoff frequency, and from which help we try to design a filter of the signal. Moving on, let's understand the concept of frequency response of a signal. It is a graphical representation that shows how a system responds to different frequencies of an input signal. It shows two plots. One is magnitude versus frequency plot, where it shows the amplitude of the output signal varies with frequency, and another one is phase response. It shows the phase shift introduced by the system at each frequency. Moving on, The two interpretations that we can draw from the frequency response of a signal, like if there is a flat magnitude response that indicates that the system treats all frequencies equally, and when we have peaks and notches indicates frequencies that are amplified or attenuated, like we can see by a plotting. Next slide. Here is the plot of frequency response of a signal. Like we can see, the peak here represents the range of the frequency. Like we have to filter. Now, moving ahead, we have visual comparison of signals, like how our signal looks. Here, the green graph shows the original signal, and the red graph shows the noisy signal, and the blue graph shows the signal after filter. Moving ahead, we will see speed signal. I've also mentioned the speed signal I have taken is of my own voice. Here are some important variables for speed signal that we can also see in the code. These are the signal plots of the speed signal I have taken. First, let's understand it by the code, then we will see the output. So, here is the code of the So here is the code of the speed signal. First, like in the sine wave signal, we have defined the sample frequency that we have extracted from the audio or the speech file we have taken. Then we have defined the timestamp of the signal. Then we will plot the signal. Then we will add noise to the signal. Here also we have add the random noise to the signal. Then we will do spectral analysis of the signal. It seemed like taking length of the signal, then defining the FFT points, then taking the FFT of a signal. Then we will also define frequency axis of the signal. In the filter, like in the design of a filter, we have taken the order of filter 5, and the cutoff frequency I have taken is from 300 to 3400 hertz. Have taken it the typical bone bandwidth of the phone voice something. ठीक है? Then we will plot the filter frequency response, and then we will filter the signal. And also we have done the visual comparison of the speed signal, like the how the signal looks before and after the noise, adding the noise and filtering the noise from the signal. Here are the output plots of the speed signal. The first one is the original speed signal. This is how it looks. And the second one is noisy signal. Like after adding the noise to the signal, it looks like this. And the third one is FFT of noisy speech signal. Then moving ahead, uh, this is the frequency response of the speech signal, which is here the peak shows the range of the frequency that we have to filter, as I mentioned earlier in the sine wave signal. Moving ahead, this is the filtered speech signal, how it looks after filtering the signal. Then we have signal comparison plots, like here the green graph shows the original signal, and the red graph shows how the signal looks after adding the noise, and the blue graph in the second plot shows the signal after filtering. Moving ahead, we have the properties of speech signal. First, we will see the properties of linearity. The first one is additivity test. Then, in this property, we divide the range of frequencies into two segments, and then we perform the filter operation on both segments. Here, after performing filter operations, we get output 1 and output 2, and the red graph, which is the combined output of both the segments. Here, we can see that the graphs are overlapping with each other. We can say that it follows the additivity property. Here we can see that first we will load the speech signal from the audio file. Then we will apply filter. Then we will do linearity test, and how it is done. We have choose the segments of the signal for testing. Then we will apply the filter on both segments, like I have mentioned earlier. And then we will generate the combined input and combined output, and then we verify. Moving ahead, we have homogeneity test. Here we have scaled the signal, and we will draw the plots, and this is how it looks, the original output and the scaled output. And here we can see that it overlaps, then we can also see that the it follows homogeneity. Moving on, we also have invertibility test. Here we can see that how the original signal looks, how the filtered output looks, and how the reconstructed signal looks. Here, the reconstructed signal or the inverse signal don't look same as the original signal or the filtered output. So we can mention that the signal is not invertible. Moving ahead, we have a stability test. For stability test, we have performed uh, two operations. First one is impulse response, and second one is step response. So, what we infer from these responses is that, like, the impulse response is decaying after interval of a time. It means the system is stable, and in also the step response, the amplitude becomes constant after a certain interval, then it shows the stability of a system. Moving on, we have applications of the noise filtering systems. We have first one is telecommunications. And telecommunications, the systems can be used for improved voice quality and for user satisfaction and communication effectiveness. The another one is hearing aids. In hearing aids, the devices like that amplify sound for individuals with hearing loss. In By using noise filtering techniques, we can reduce noise and filter out useless noise. Then we have speech therapy. We can also use noise filter techniques in speech therapy. The benefits are we can filter noise in recordings for clearer analysis and feedback. Aids in targeted therapy for better speech improvement. Here we will end our presentation. Thank you, everyone.